Of hydroxyl on the moon. Tom? You will be gonged at 10 minutes. All right, I'd like to thank everybody for the opportunity to give you an overview of some of the work we've been doing, particularly in the Vortices program, or the survey network there. It's an overview of a long-standing collaboration with Carl Hibbets and Darby Dyer. And I want to introduce some work that's been done recently by Alex Alexandrov in the modeling of what's going on when the solar wind interacts with regolith. Okay. What's the thing on the right? Oh, no. The thing in your hand. Okay, good. All right, so looks like okay. So I'm going to give you an overview, and there's going to be some background on the first two topics, which is thermal desorption of molecular water on the lunar regolith, photodesorption of molecular water on lunar regolith. And the bottom line for these two topics is that water does not really stick very well at temperatures typical of the moon. Okay, and then we'll move on to modeling the solar wind interactions and looking at temperature dependencies of optical signatures, and in particular, the optical signature between 2.8 and 3 microns, which I would argue, and a number of people have already said this, it's likely due to proton implantation, but that proton implantation, from our perspective, makes pretty much hydroxyl groups. And then you can model the temperature dependence of that optical signature by looking at a simple first-order degradation process of the hydroxyl groups that are produced by the solar wind implantation. Okay. That's basically the talk, so if you want to take a rest for the next 10 minutes, you can. All right. Now, we've developed and built this machine solely to do TPD of water on lunar regoliths. And so we built a system, and it's novel in the sense that it allows us to do powders, which normally surface scientists do single crystal work. And so TPD is a very standard technique in surface science. So we have an ultra-high vacuum system at 10 to the minus 10 torr. And then we have this detachable liquid nitrogen dewar right here. And then we have an effusive gas dosing system here and a very controlled heating element here. So we can detach this, heat only the surface, and then we measure very carefully the rate of release of the water from the regolith surface with a controlled heating rate. And from that, we can back out what the binding energies are. Okay, and that's a TPD spectra. Okay, now, this plot here is one that I really would like you to understand. It's one of the very first measurements we did when either Darby or Carl, I forget who sent us this sample. We took the sample as received. There's no water added. We put it in our UHV chamber. It's sitting at room temperature. We do a TPD measurement. So we measure the removal of mass 18 water as we slowly heat up this L-bite sample. You can see a little bit of water comes off, then there's a little bit of shoulder here, then there's a very large increase in the water release rate. Okay, that's turning on around 450 Kelvin, peaking at about 600, it's gone at 750. This is a very important plot for the rest of the talk. So this here is a little bit of chemisorb water that's coming off. It's all coming off as molecular water, but it turns out that this water here at high temperature, the peak above 400, could be, and we're rather certain it is, due to recombinant desorption. There's a word missing here. We are removing the OH groups. So basically, these are the OH groups that are part of the regolith, that as you heat it up to high temperatures, it makes water. Okay, that is not to say that I think that there's any water made on the moon from the solar wind, okay? Because the solar wind comes in, it makes OH groups, but the moon surface never gets to this temperature. Now, I've taken this sample, which I took all the way out to 750 Kelvin. I remove my OH groups. I then very carefully control the amount of water that goes onto the surface, less than a layer. And then I do a TPD measurement. This is the purple thing. Here's little multi-layer waters. They're actually little balls of water on the surface. And then there's this bump here, which is this chemisorb water here. And then it goes down. If I take another sample, which I only heat it to 500, do the same measurement, I get this blue here. There's multi-layer water, the chemisorb water, and then I get the recombinant desorption. Okay? 3 types of water. Physisorb ice, multi-layers, chemisorb water, recombinant desorption. These are OH groups. Okay. So then we go and we do this on the actual lunar samples. And we basically heat those up to 550 and then do the same measurement. So this is the data from the sample. This is the blank. This is the subtracted sample. So this is the data that's coming only from the regular sample. Okay. We do it for many different coverages, and we can then do a standard kinetic analysis and extract out what the binding energies are. Now these are two different samples. One is an orthocytic soil, a highland sample, 72501. Then one's a low titanium soil, a Mare sample, and you can see there's a vast difference in the amount of water that they take up. Okay, this being significantly higher. There's essentially no chemisor water on the titanium sample. Okay, so now we have this data here, and we can analyze it with the standard TPD analysis and Polanyi-Vigdor kinetic analysis and extract out a binding energy. Okay, these are the binding energies that Bill Farrell needs to add to his model when he's looking at the sticking of water on airless bodies. Okay, so this is the binding energy distribution that you extract out of that, and it's sort of peaking here about 0.7 eV. Water on itself, or the water-water interactions, is just a half an EV, a quarter of an EV per hydrogen bond. So it's slightly bound more than water to itself, and then you have some states, but not many, that have higher binding energies. I'll get to this at the end. Actually, this width is a little bit narrower because we did some analysis where we have a diffusion component that's taken into account that narrows up that width a little bit. Okay, so then with that binding energy, you can back calculate what the cumulative amount of water is. And you get out to somewhere around 75 ppm. And this is just from thermal sticking. Okay, and then you get a little bit more. You can integrate this and you can get a total density. All right, one thing that's useful, and I would call this a zero order model. You take this binding energy, you take these thermal activation energies, you have your desorption rates, and then you can put them in a model and just say, how long will the water stay on a typical lunar cycle? And the bottom line is it doesn't stay on a typical lunar day. Okay, so if you look, if you look at these lower mid-latitudes, you'll find that it just goes away, and not until we get closer to the poles where you get temperatures where it's high enough to where you can have some sticking. Okay, that's thermal desorption. There's another thing that's going on, and it's photon bombardment. So let's look at photon-stimulated desorption, because thermal desorption is just that. It's a thermally driven process. This is actually a non-thermally driven process, and there's plenty of photons hitting the surface, energetic photons in particular. So we took lunar slabs here. We have an impact melt breccia and a Mare basalt breccia. This is the composition from the table. And the experiment here is I have a laser that goes straight on in the center of that, in that red circle, and then there's another laser that skims across here. So this is a two-laser experiment. One laser on, one laser in front of the sample. So you knock off the water, and then you photoionize the water, and you detect it, and you basically can detect and count the number of water molecules that are coming off. So with a known flux, you can measure the total cross-section, the absolute cross-section for removal. This is not too important. It's a pulsed laser, one laser pulse here, this fires here, and we're able to do this by taking advantage of some nice spectroscopy where we can do selective ionization of the water. We can get the total amount of water, how much it's vibrating, how much it's rotating, what angle it comes at it. You don't need all that, okay? You can to get a cross-section. Okay, cross-section is large. This is an interesting thing. The cross-section for photodesorption of water off of an impact melt breccia and a Mare breccia is pretty high. 5 times 10 to the minus 19, almost 10 to the minus 18 square centimeters. So the thermal desorption cross-section rates are high, and the photon-stimulated desorption cross-sections are high. So again, based on this, water really shouldn't be sticking around in the sunlit surfaces. So what is the solar wind doing? So this gets back to a very good talk this morning where we were looking at the solar wind cycle. Dana Hurley gave a very good overview of this. The idea is similar, okay? We need to look at this in terms of a cycle. We have a solar wind implantation of H+, that should be H+. It deposits its energy in a very, very short skin depth, 20 nanometers or 10 to 20 nanometers. And then when it does that, the energy loss, the straggling, is first its neutralization, but then it's actually reaction. And then it ends up making an OH defect, Okay, this is the OH production. Okay, now that'll be a little bit dependent upon the latitude because the flux is latitude dependent, and then the temperature. Now, when this comes in and it makes a hydrogen atom, if the hydrogen atom doesn't form an OH, what it'll do is it'll rapidly, and this moves really fast, it'll find another hydrogen and make H2 and leave. Okay? So what we really have to care about is the hydrogen that doesn't leave, and that's tied up in the form of an OH group. And then we have a temperature cycling of what would be stable OH groups, and we got to watch how that hydrogen moves. So that's hydrogen diffusion through a OH group. Okay, so what we have to pay attention to is this. That OH will be lost by photodestruction in a reaction with a hydrogen atom. Okay, so this is a picture of what we were talking about already. The proton comes in, it makes all of these termination groups. I was very interested in the previous talk. There's an assumption we have here that this turnover and grain turnover and charging and deposition doesn't change the story, so maybe we're wrong. But anyway, so we're starting out with this. This reiterates the fact that you don't get rid of these OH groups at normal temperatures that the moon's having excursions over. So we really don't have this as an option. Okay, so I have a model. What I did is I have, okay, proton implantation, thermal transport, loss channels involving chemical reactions and photolytic processes. So we have a series of analytical solutions of a non-stationary diffusion equation to approximate the real space-time H and OH distribution. So we put in this diffusion model, we added something which is new and important. We put in these pseudo first-order loss terms, which are the removal of this. We assume that this is reaches saturation, and then what we have is these two prominent loss terms, which are a chemical reaction and a photodestruction. They're first-order losses. Okay, so when you do that, you get a distribution function, which is a concentration versus depth. Okay, and this is the diffusion on there too. Unfortunately, this did not come out very well. There's a dotted line and a solid line. The dotted line is the diffusion only model, and this is a big deal. So if there's anybody in the community who knows a better number to use than this, I want to hear it. We're using the diffusion constants for hydrogen atoms and fused silica. Okay, so the dotted lines are up here, here, and here. Okay, and you can see that you have a loss rate. Now I add pseudo first order losses, and the dotted line and the solid line lie right on top of one another. But if I do this simulation for 1,000,000 years, there's a huge difference in the buildup rate based on the fact that I have now this pseudo first order loss rate. So on 1,000,000 years it matters. Okay, so these are the rates. Those don't matter. The two that matter are 5 and 6. And this is the plot that I think people might be interested in. I'm done. You can get the latitude dependence of the profile and temperature distribution, and this changes as you go from 10 to the 4 years to 1,000,000 years. In 1,000,000 years, you get a pile up on the poles. And so this actually simulates the data that's in the literature pretty well because you have these loss terms. So thermal desorption, photodesorption makes water not stick. Temperature dependence can be found in this degradation process. And we redid this model for mercury. And there's massive differences. Even though there might be similarities, there's massive differences with regard to the production probability of water on Mercury versus the moon. Water is made by this process on Mercury. Okay.
Why the returned lunar samples we don't see these hydroxyls in the rims of the lunar grains, and maybe this is because we collected these samples from the lunar equator, and these loss terms can explain that. So do you think if we collected samples from higher latitudes that we would be able to see hydroxyl in the rims around the lunar grains?
So it depends on how deep into the rim you want to look. So the hydroxyls that we're looking at are within 2 to 3 layers thick, right? And so they're really superficial. And then if you have a really porous material and you're able to get in there, they should be at the surfaces of the pores. Frankly, to be honest, we've never looked at a metal oxide mineral that is not hydroxylated. If you look at the level at the very terminal surface.
But that could be due to contamination from Earth atmosphere as well, right?
Well, yeah, sure, that's what it's from. It's water interacting with the mineral because they're very active. And so that's actually why we moved and we did the very first experiment and took it to 750 to move stuff off.
Yeah.
And then we do all the experiments at 550 because then you've removed all of that, right?
Can't help myself. This is really good, Tom. Let me ask you a question. What activation energy did you use in your model, did you assume? So you had the diffusion coefficient, which was, I think, 10 to the minus 11 meters squares per second, but what kind of activation energy did you use?
That's a good question. So like any model, there's adjustable parameters. The one that really is a problem is the diffusion constant, right? And we use that one. You know, if you use the one from Illumina, it's like 10 orders of magnitude different. So what is the one for lunar regolith? This is what I want to know. I have not found that in the literature. So the other adjustable parameters are the rates. Okay, so we don't have activation energy for diffusion. We just put in that diffusion constant, right? But we do have some activation energies where we're looking at the rates of the first order loss processes. Okay, and in those cases, we put in an activation energy, which is not on anybody's screen here, but it's related to charging of grains. We put in the activation energy to release a trapped electron, and that's about 0.2 eV. Okay, other than that, there are no other activation energies.
Well, let me ask you, if you put a spread in that, made it 0.2 to 0.6, would you might get, it'd be interesting.
It does. It changes. And, you know, and the 0.2 is a number we got out of the literature for trapped states in glass. But the problem, you know, so I don't want to go too far in the range because I actually think that the photodestruction cross-section is the thing that's dominating it, and that's not activated. That's a photon in an excited state, and it dissociates. So,
Interesting. All right. Yeah.